Hello and welcome back to Math Quest. I'm Professor Cunningham, and oh hey look, I'm in the bottom corner now. This week we're going to tackle the very difficult question of whether math is something that we invented or is it discovered. Spoiler alert, it's kind of both. I really ought to get a title screen or a logo or something. I'll see what I can do for next week. Anyway, we know that numbers are a construct made completely by humans. After all, we made some together last week. But it can be difficult to write math off as something that we just made up. Math can be seen just about everywhere. Mathematical patterns pop up in nature all the time. We can use math to build incredible structures. It was used to estimate the circumference of the Earth more than 2,000 years ago. It can even predict with reliable accuracy the movement of heavenly bodies like Halley's Comet. Math is the basis for much of the art and music that stirs our souls. When you take all of this, along with some of the astonishing relationships and coincidences that occur between seemingly unconnected numbers and ideas, it can sometimes feel like math is some sort of universal truth that is being revealed to us a little bit at a time. But is it though, or are we just fooling ourselves? This video we're going to take the rock-based number system that we created last time, along with a couple of simple ideas like addition and multiplication, and just kind of see where they lead. Fair warning, I will be throwing some vocabulary at you, but feel free to let it drift in one ear and out the other if it makes you stressed out. There is no quiz here, and all of the words that I use today I will teach you again in later videos. I just think it's important that you get some exposure to the kind of terms that you'll be seeing in your math classes as early as possible. Besides, last time we found out how much easier ideas are to talk about when you have names for them. Alright, let's get started. Last week we built a system to keep track of how many sheep or rocks or fish that we have in a particular group. So here we are again with a bunch of sheep. Let's say you have 1, 2, 3, 4, 5, 6 of them. But you go to market and you buy 1, 2, 3 more. How do you figure out how many sheep you have now? Well, that's an easy enough process. We're going to put this symbol we'll call plus in between the two numbers just to show what we're doing. But really all we need to do is put the sheep together and count them again. 1, 2, 3, 4, 5, 6, 7, 8, and 9. 9 sheep. Do we really have to start all the way over from 1 when we count them? That seems like a hassle. We mathematicians hate having to do the same work twice if we can avoid it. We're just lazy that way. No, I mean efficient. Here we've got a pile of 1, 2, 3, 4, 5 rocks, and we're going to add another pile of rocks. But instead of putting them together and starting over from 1, we'll just start from the number after 5 and continue the count. 6, 7, 8, 9, 10, 11. 11 rocks. So 6 rocks plus 5 rocks is 11 rocks. Haven't lost anyone yet, have I? Let's double check to make sure that's right. We put the piles together and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 11 rocks, just making sure. Anytime you come up with a new method for doing something, it is important to check it against the old method and make sure you get the same answers. This is a theme that's going to come up over and over and over again in this channel, so get used to it. So here we've created the idea of addition. For our purposes, we will define addition as taking 2 piles of rocks, putting them together, and counting the result. Yes, the actual mathematical definition of addition is much broader than that, but for our purposes, we'll just leave it like this, and when we learn more later, we'll update our definition accordingly. Speaking of updating definitions, does it have to be 2 piles of rocks? Could we add more piles of rocks than just 2? Of course we can. Here we have 1 pile of 4 rocks, 1 pile of 3 rocks, and 1 lonely rock that wants friends. We want to add them together using our putting piles together method, but I'm kind of stuck. So far our definition only covers 2 piles at a time, and I don't know where to start. Well, here's another thing I'm going to say all the time. Let's try something and find out. I could start by putting this pile with this one and getting 7, then put that group together with the group of 1 to get 8. But what if instead I took these 2 piles and put them together to get 4, then I could put these 2 together and get also 8. Surprised? Of course not. After all, we knew there were 8 rocks altogether, regardless of how we go about combining the piles. However, this is a big deal, and this big deal has a name. It's called the associative property of addition. If we have 3 or more numbers that we want to add together, and we indicate with these parentheses which ones we want to add first, it turns out that we get the same result either way. By the way, the word associative comes from the word associate, which means to group together. Turns out most of these names do actually make sense when you break them down and really look at them. Similarly, notice that the same thing happens if we take 2 piles of rocks and reverse the order. Here we have 5 plus 2 and 2 plus 5, and unsurprisingly, they turn out to be the same thing, 7. It turns out, to the surprise of no one, that it doesn't really matter how you organize the rocks ahead of time, all that matters is how many there are in total. We call this the commutative property of addition. Usually we use the word commute to describe going back and forth from work, so in this case we're going to use it to indicate that you can do the addition in either order without changing the result. When you look at them this way, these two properties seem super obvious. But are they, really? If you were just told about these properties without being given piles of rocks to look at, would it still have been so obvious? By the way, I make a silly arithmetic error here. For just a second, I thought that 7 plus 4 is 12 instead of 11. I caught the error right away, and I could have taken it out of the video, but I left it in there because it's super important to know that anyone can make silly mistakes, especially if you're trying to go too fast. Making arithmetic mistakes is absolutely not something to be ashamed of, but it is something to be careful about. Always double check your work and make sure that all of your arithmetic is correct. Anyway, these properties seem a lot more discovered than the original numbers that we created. We didn't set out to create a system that followed these rules, we just wanted a way to make sure we knew how many sheep we had. There is nothing saying that we had to define addition this way, and in fact, in other classes, you may end up defining addition differently. But the moment we defined numbers as the amount of rocks in a pile, and addition as putting two piles together and counting, these two properties became natural, inevitable consequences. They couldn't not happen. That feels a lot more like discovery to me. So let's keep playing with these numbers and see what else we can find out. As I'm messing around with these piles of rocks, I realize that some of them can be put into the shape of a square, and some of them can't. Looks like I can make squares out of 4 rocks and 9 rocks. What if I wanted to make a bigger square? 16. This is neat, but I don't really know what we're going to do with it, so let's just call these numbers square numbers and move on. I am interested in other ways these rocks can be arranged, though. I noticed that if I organize them into 2 rows, I really only have 2 possible options. Either they line up perfectly with each rock having a partner, or there is exactly 1 rock left out. Since 4 rocks and 6 rocks line up nice and evenly, I'll call them even numbers. 7 and 9 here each have a sort of an odd man out rock, so we're going to call those odd numbers. Now that we've created these definitions, let's see where they lead. To start, let's look at addition again. Looks like if we add 2 even numbers together, the result is going to be even. That makes sense, right? If neither group has an extra rock left over, then one isn't going to magically appear when you put the 2 groups together. It's important to note that this works no matter what even number we choose. I'm going to put these 3 dots in between these pairs of rocks to indicate that there is some unknown number of pairs in between. In other words, this even number could be as big or as small as we want. And yet, when we put the 2 together, we still always get an even number. Again, we didn't set out for this to happen, we didn't do it on purpose, but once we defined even numbers and addition the way we did, it couldn't have gone any other way. So what about adding an even number and an odd number? Or 2 odd numbers? Will those also have predictable and inevitable results? If so, what will they be? I'm going to step back for a few seconds, and I'd like you to pause the video, grab whatever objects you have close at hand, and try this out for yourself. Find out what happens when you take an even number and an odd number, or 2 odd numbers, and combine them. Be right back. And we're back. So, when you tried this on your own, which you did, right? You probably realized that when you took an odd number and added it to an even number, that lone rock in the odd number isn't going to find a partner amongst a bunch of even pairs. So the result is always odd. However, when you add 2 odd numbers together, each number has 1 unpartnered rock. They can find each other and create a nice even number. Again, no matter how many pairs of rocks there are, if each one has 1 single rock and that's it, then those 2 rocks form a pair and create an even number. So an odd number plus an odd number is an even number. Also ignore that 1 rock off to the right. I didn't mean for it to be there, it probably just wanted more screen time. Okay, so it's all very interesting to organize rocks into 2 rows, but does it have to be 2? How else can we organize these numbers? This pile of 12 rocks up top can be easily organized into 3 rows of 4 rocks each. But this pile of 10 below has 1 left over when we do that. Here's a pile of 20 rocks. It can be sorted into 2 rows of 10 nice and neat, but when we try to put it into 3 rows, there are these 2 rocks remaining. We should come up with a name for these remaining rocks. Let's call them leftovers. No? Remainders? Well, anyway, let's move on. Anyway, we're able to put it into 4 rows without any trouble. Maybe there's something to this. Some piles, like this pile of 7, don't seem to be organizable at all. No matter how many rows I try to put them in, there always seems to be some remainder. Well, I guess I can put them into 1 row. Well, it's certainly possible to make 2 rows of 7 each. But 7 itself seems to be some kind of special number that can't be broken down into any number of equal rows. We're going to call this special kind of number a prime number because that's a cool sounding name. Maybe we should also come up with a name for the other kind of number. Since these numbers can be composed of rows of smaller numbers of rocks, let's call them composite numbers. And we'll define a composite number as a pile of rocks that can be organized into equal rows. Again, don't worry about memorizing these vocabulary words right now. If you've already forgotten about them, that's totally fine. The names themselves are less important than the idea that some numbers can be organized in this way and some numbers can't. This pile of 12 can be organized into 3 rows of 4 rocks each. We'll use this little X symbol to show that. Since we're talking about multiple equal rows, we're going to call this process multiplication. I don't know about you, but the way this video is going so far, I'm super excited to see where this multiplication idea leads. For example, here's 2 rows of 5 rocks each for a total of 10. But I also notice that if I take 5 rows of 2 each, I also get 10. Basically, I just took the rectangle and turned it sideways. This seems very similar to what we did to get to the commutative rule of addition, so let's call this the commutative rule of multiplication. In other words, just like with addition, you can take 2 numbers and multiply them in either direction and still get the same result. This isn't some complicated theorem that you need to memorize. It's just a consequence of making rectangles out of rocks and turning those rectangles sideways. Okay, so I've thrown a lot of big ideas and used a lot of big words in this video. So instead of throwing more vocabulary at you, I'm going to take a couple of steps back and give you 1 or 2 more simple examples of neat properties that come out of this system. The first example comes directly from the book The Joy of X by Stephen Strogatz. If you're watching and I mispronounced your name horribly, I am so sorry. Just for fun, we're going to start with the number 1 and then add each odd number to it in order. So 1 plus 3 is 4, 1 plus 3 plus 5 is 9, 1 plus 3 plus 5 plus 7 is... I don't know about you, but these numbers are starting to look awfully familiar to me. Let me check back earlier in the oh, yes! These are the square numbers that we looked at earlier. How in the world did these square numbers come up just by adding a bunch of odd numbers together in order? This seems like an extraordinary coincidence. Is this proof that somehow math is divine in some way? As before, we're going to take a look at piles of rocks and see what happens. So we start with 1 rock, which is a square number. And let's say we want to make the next bigger square. How do we do it? Well, we put 1 rock to the side, 1 rock below, and 1 rock in the corner. 4. Want to make it bigger? We add 2 rocks to the side, and 2 rocks to the bottom, and 1 rock in the corner. We've added 5 rocks, and we're at a total of 9. Do you see the pattern? To make it bigger still, we have to add 3 rocks to the side, and 3 rocks to the bottom, and again, 1 rock in the corner. We're adding 7 rocks, bringing us to a total of 16. Every time we want to make a bigger square, we have to add the current number of rocks on each side twice, once to the side and once to the bottom, and 1 more in the corner. We'll find out later that this is exactly the definition of the odd numbers. Nothing divine about this. Just like almost everything else we've talked about this video, this is just a natural consequence of the numbers as we define them. Okay, 1 more brain teaser before I let you go. There is a very famous story that is told to every math student at some point in their lives. The story is about a young mathematician named Leonhard Euler. Or was it Euclid? Einstein? Well, the names changed from teacher to teacher, but the story itself remains basically the same. The idea is that a teacher of a bunch of young kids wanted to take a break really quick. So he set the students a task that he figured would take them a while to work out. Add up all the numbers from 1 to 100. As the students get to work, he kicks back in his chair, opens the newspaper, and figures he's going to have a fair amount of time to just relax. So imagine the teacher's surprise when our mathematician comes up with the answer in just a couple of minutes. Imagine the teacher's further shock when they find out that the answer is correct. How did our mathematician figure this out so quickly? Once again, I am going to take a step back for a few seconds and give you a little bit of time to pause the video and try to figure this out on your own. However, before I do that, I'm going to give you a couple of hints. First off, keep in mind the associative and commutative rules that we've already learned today. Secondly, keep in mind that mathematicians don't like doing repetitive work. We don't want to do the same thing over and over again. We want to solve the problem in the most efficient way possible. BRB. Now, I'm sure this was a tricky one for most of you because we aren't really taught to play with numbers this way. From the very beginning, we're taught that math is serious business and we have to be serious about it, and if we're not serious about it, then we're going to get a bad grade. But once you begin toying with the numbers, it turns out the solution is a lot simpler than it looks. Let's take the first and last number, 1 and 100, and add them up. 101. How about 2 and 99? Also 101. 3 and 98, 4 and 97, they all add up to 101. This happens all the way up to 50 plus 51, also 101. So instead of painstakingly adding each individual number together, we can just take 101 50 times and get our answer, 5050. But here's the thing, even if you don't know how to multiply 101 times 50, there is still a way you can organize this so that you can solve this problem. Instead, we'll just start at 0. 0 plus 100 is 100. 1 plus 99 is 100, all the way on up, until you get to 49 plus 51 is 100. You get 50 sets of 100, which is 5,000, and then you have 50 left over. 5,050. The idea here is that math has a playful side too, and doesn't always have to be taken so seriously. Puzzles like this can be a nice, low-pressure way to explore numbers, figure out how they can be manipulated and put together in different ways, which will make your serious math courses later much easier. For now, let's wrap this video up by trying to answer our original question. Is math made up, or is it discovered? We certainly made up numbers and numerals, but I'm not so sure about the concept of cardinality. I mean, it seems like something that exists outside of the human perception of it, but I'm not entirely sure, so I'm going to put it in this far column. I am sure that once we came up with the idea of numbers, we discovered the existence of certain types of numbers, like even numbers, odd numbers, primes, composites, square numbers. We made up the names for them, sure, but they existed on their own based on the definition of numbers that we came up with. We made up addition by defining it as putting piles of rocks together and counting them. But then we discovered that because of our definition, the order and grouping of rocks didn't matter when it came to calculating the total. Same deal with multiplication. So in the end, unsatisfying as it is, I'm going to have to put math down in this third column. When it comes down to it, some of the definitions are definitely things that we came up with, but a lot of the other ideas are things that we discovered as consequences of those definitions. And knowing the difference is very important. The definitions of things that we made up can be tweaked or modified, and then you can explore the consequences of new types of mathematics. For example, you learn early on that you can't subtract a larger number from a smaller number. But later on in school, you get to ask yourself, well, what if I can? And in asking that question and exploring its consequences, you get to look at an entirely new realm of mathematics that didn't exist for most of human history. Being able to ask this question and explore what-ifs is what allowed us humans to slowly build up our knowledge of mathematics over the course of thousands and thousands of years. Thankfully, you and I don't have to do that. We don't have to start from nothing and figure it all out on our own. You and I get to benefit from countless mathematicians going back thousands of years to figure this stuff all out for us. All of which eventually led to you and me right here. That's what you're learning when you're learning math, and that's why I get so excited about it. To me, learning math is like taking a time machine back to those days when these ideas were new, and seeing through the eyes of philosophers and scholars who were just trying to make sense of the world, and doing so in the most beautiful way I can imagine. Well, that's all for today. Next time we're going to tackle one of the most daunting ideas in all of mathematics, infinity. Until then, I hope you will like and subscribe if you haven't already. And if you can, please consider supporting me via Patreon or Ko-fi. I would love to increase the audio and video quality of these episodes, but new cameras, microphones, and studio lighting don't pay for themselves. Thanks for watching, and always remember that I believe in you. I'll see you next time.